So we're in business. I'm going to play a video for you. It's kind of a hokey little video I made up a while ago, and it's concerning how this idea of looking at the variance, the variability of the numbers in samples can help us determine whether the means are really different. Okay, so let's think about it this way. When we do a t-test, we're comparing the means of how many groups? Two, right? Group one and group two, right? Because we're going to subtract one mean from the other, or one percentage, one proportion from the other proportion, those 2 point estimates, those two means. And how do we determine the likelihood that they're really statistically different? We don't really look at it in terms of the actual numbers, like for instance, if the average blood pressure in one group is 105 and the other group is 110, we don't look at it just in those terms. We use those numbers to determine how many standard errors apart they are, how likely that we would, in these two samples, get that big a difference if they're really taken from two different populations. Right? So we're looking for a distance in terms of standard errors, in terms of the likelihood of getting that number, that mean, those two means being that far apart, not necessarily in terms of their absolute values, but in terms of what we would expect the means from a sample size from the same population to be if they were different. Okay, so now sometimes we deal with a situation where we want to compare more than three groups to one another. Like for instance, let's say I wanted to compare blood pressures of different ethnic groups in New York City. Do Hispanics, on the average, have higher diastolic blood pressure than, say, Caucasians or from blacks or from Asian Pacific Islanders and so on and so forth? Let's say I had 6 different ethnic groups that I was comparing. And I wanted to compare the mean blood pressure for each of those groups. And I took a sample, say, of 100 people from each of those 6 groups. Now, if I wanted to use the t-test to do that, how would t-test only works for 2 groups at a time, right? So I'd have to take those 6 groups, let's call it group A through F, right? Group A through F. I'd have to run a t-test on A and B, right? Group A and B, see if they're different, then A and C, then A and D, then A and E, and then A and F. I'd have to run 5 t-tests. Well, now I still haven't compared B to C. So I have to go back and run another 4 t-tests, B to C, B to D, B to E, B to, right? And then I have to go back again and run C to D, and so I'd have to run it multiple times, 5 times 4 times 3 times 2. I'd have to, whatever that comes out to. What does that come out to? About 30 or so, 20 or 30, right? So how much is it? I don't think so, right? 5 times 4 is 20, times 3 is 60. You're right, 120, 120 times, right? Not quite, because there's going to be, because remember, comparing D to E and E to D is going to be the same, so we're going to divide it by something. But let's not worry about that right now. We got to run it a lot of times. Each time I run the t-test, what's the probability I'm going to be wrong? If I set alpha at 5%, right? I have a 5% chance I'm going to be wrong, right? So if I keep running it over and over again on the same data, right? Eventually, I'm going to reject the null hypothesis, possibly when I shouldn't reject the null hypothesis, not at the level of error that I find acceptable. So we have a problem with using the t-test the way we normally would do, to run it for multiple times on several populations for the same values, right? So instead of that, we need another test that'll account for that. Okay, and in fact, we need another test that perhaps will also save us the trouble of having to run a t-test multiple times, right? And that's where analysis of variance comes in. Okay, so now we call it analysis of variance, but it's really comparing means, right? We use it for numerical variables, and we use it to determine whether there is a significant difference between the mean of multiple groups. You can use it for 2 groups, right? We'll talk about that at the very end. Maybe we'll even get a chance to examine what happens when you use it for two groups, because it's kind of interesting what the kind of the result that you get when you use it for two groups. But most of the time, we're using it for three or more groups, so that we don't multiply the likelihood of us making an alpha error of rejecting the null hypothesis when we shouldn't be rejecting the null hypothesis, and also saving us a lot of trouble as we're going through. So now let's get our head around this. We're going to use the variance within these groups. Actually, we're going to use two variances. We're going to use the variance within the groups, and we're going to use the variances between the groups, and we're going to examine those. So what do I mean by that? Well, first of all, if the means are far, let's say group A, group B, group C, group D, group F, and so on and so forth. If the means are far apart, it makes sense to us that it's more likely that the population means are also different, right? If the means are close, if I take a sample from group A and group B and group C and group D, and the mean is 100 and 101 and 101 and a half and 102, well, they're not very far apart. But if the means are 90 and 100 and 130 and 240, those means are from those samples. Those means are further apart. And I'm more comfortable that the means in the populations may be different, right? Now, there's another problem with this, though. What if within the groups, there's a lot of variability? Well, all of a sudden now, if there's a lot of variability within the groups themselves, that means I can't be that sure of what that means for each one of those, whether that sample for each of those groups really was close to the actual population mean for that group. So what I really would like is I would like for these groups to have means that are far apart from each other. But within each group, I would like to have the numbers within those groups to be very tightly clustered, to have very little variability, right? So what does that mean? That means if the means are far apart and there's very little variability within each one of the groups, I can be pretty sure that the means of the populations are different. But if the means are close together, or if the variability within each group is very large, there's more overlap. I can't be quite as sure that the means in the population are different from another. So I'm going to play this video. It's on, the link to it is online for you guys that want to, if you can't see it while I'm playing it here, guys that are online, you can actually just get that link and open it on your own. Let's see, here we are. Okay. Okay, Levi, you're joining the online group today. Good, yeah. Great. Okay, let's see, where am I? So I'm going to play this and see if I can't get it to actually give us a noise in the background, see if the audio is working in the background there. Hopefully it is. It's on mute. What's that? It's muted on there. Yeah, I'll get to it. Okay, let me open this up. Get to the video. I may actually have a copy on here I can play. Oh, it's playing. I don't hear nothing. And it's not muted. My volume's up. Volume's up here. Oh, I hear it. That's yours? Can you play it? That's loud? That's the loudest it goes?
Well, what if like 4 people started at the same time?
That might be a little tough to get that timing down, I think. There might be a little bit of an echo.
Is the volume up on the actual video?
Okay.
What's it
Tell you what,
to?
I'm going to narrate it. Okay, so I think that'll work. Okay, let me narrate this thing. I'll get started again. What's that?
Yeah, click the volume. The volume on the actual YouTube.
No, it's all the way up. I think it's this unit. I think I had a problem with this once before. I think I meant to call ICID about this thing. I don't think the audio is working on this PC.
Yeah, no, I knew that, and
They were supposed to fix it, but I guess they never got around to it. I'll narrate this thing. You can always play it at home, but you'll hear my live narration of this. Let me see if I can't get this to blow up here and fill the screen. Where is it? Okay, now I'll get started again. Okay, first of all, this is the New York Botanical Garden, the Brooklyn Botanical Gardens. Every spring, they have like 200 or 300 cherry trees, various varieties. And they have a cherry blossom festival there in the spring. And these things all bloom around the same time. They actually have a website where you can actually see how many of them are in bloom at any given time. So if you ever get a chance in the spring, usually around March or April, go to their website to have a little chart that shows you how close each of the trees are to bloom. Okay, so now, they're clustered in different groups. They have two enormous rows of these things, really spectacular. So at any rate, one of the things I noticed about them is they had basically a lot of different varieties. Some of them were very, very wide, right? And the blossoms like spread out quite a bit. Others, the trees were very narrow, and the blossoms were straight up and down, and they didn't vary. They didn't spread out that much. Now, the ones where the blossoms were spread out very wide, it was actually hard to tell the trees apart. You couldn't see where one tree started and the other tree ended. The ones that were very narrow, you could actually see a space between the trees because the blossoms didn't spread out that much. Okay, so if you look at this, it kind of reminds you, that shape reminds you of a normal distribution, right? Doesn't it? Right? The tree trunk is kind of like the mean, right? And the blossoms are spread out, and they're kind of like the way it's distributed. Like those wide ones had a very high variability, right? So it's hard to tell apart. So the tall narrow ones had so with the wide ones, you really needed the tree trunks to be far apart to see a space between the individual trees, right? The narrow ones, you didn't need that much space between the narrow ones, right? Because the variability, those blossoms didn't go out as far, right? So it was easier to tell between one tree and the other tree. So it's kind of like analogous to with what's going on with our analysis of variance. If the distribution in the population is very wide, there's a lot of variability, you need those means to be far apart in order to distinguish between the groups. If the variability is very small, so now we want to create something that, we want to create a measure that will tell us whether or not the variability is big enough. If the distance between the means is big enough for us to be able to distinguish between the different groups. Okay, so let's invent a statistic, right? And that statistic is going to be a bigger number if there's if there's very little variability is a good thing. So we want a bigger number when there's little variability, but we also want there to be a big distance between the two of them. So we want a big distance but a small variability, and we want both of those factors to make that number a bigger one when we have what we want, and a smaller number when we don't have what we want. So let's take a look at that number. So we're going to make a ratio. On the top of it is going to be the variance of the means, the distance between the means, the variance between the means themselves, 10, 50, 90, whatever the means themselves are. So it's on the top. The bigger the variance between the means, the distance between the means, the bigger this statistic F is going to be. Okay, so now what about the variability within the groups themselves? Well, the variance within the groups, we want that to be small, right? So if it's a small number, it means that F number is going to be bigger because it's on the bottom. If the variance is big, right, it makes the F number smaller. So now that F is going to be larger or smaller depending on whether or not we get the right ratio between the distance between the means and the variability within the group. So we're going to call that F. As the value of F increases, it's less likely that the means of the groups are from different populations, that the populations have the same means within those groups. Okay, so there is actually a distribution that's connected with this. Okay, and this distribution for F, is for the analysis of variance. Now, this number, right, is never going to be less than 0, right? So we're going to start down at this end over here at 0. So this represents the probability that we would get this big an F number, this big a value for this statistic, if these groups, if the means of these groups, the populations rather, that these samples were taken from, are the same. In other words, if my null hypothesis is true, the probability, so what we want to do is we want to get an F number that's big enough that there's less than 5% chance that the means of these populations are the same. Okay, so we're looking for this area up here to be less than 5%. Okay, would you call that a one-tailed distribution or a two-tailed distribution? One-tailed. You know, I was thinking about that because SPSS always calls it a two-tailed distribution. And even though this only has one tail, have we made any qualifications about whether group A is greater than group B or group B is greater than group A? No, we haven't. So it really is still a two-tailed test, right? Even though this distribution only shows us one tail, it's really cumulative for both tails. That's why I believe that's why SPSS calls it a two-tailed test, even though this is the distribution. Okay, so we want that F score to be big enough that we can reject the null hypothesis with less than 5% chance of being wrong if we reject the null hypothesis. So we're going to calculate that F score. And that F score is going to be based on it's going to be based literally on the variability within the means and the variability within the groups and the variability between the means of the groups. Okay, so we're going to actually go ahead and do a calculation like that. So now we're going to do it manually here in class. Okay, and I think, did I finish that? I'm not sure I finished that. I'm not sure I let that finish.
The F score is marking the rejection region.
Yes. Yeah. Okay. We'll get to how to calculate the F score and what it actually means in a second. And I'm sorry I stopped that at that point because I think there was a little bit more there. I'm not sure. Oh, where did I put it? Let me just make sure I don't have any more there. Where'd it go? There it is. Okay, and again, you'll actually be able to play with some sound later on. And my voice, I think my voice is a little dramatic in it, so we'll try to ignore that. Frustrated actor, I guess, When he's up. Okay, it's not cooperating though. Oh, okay, let me see if there's any more of this. What's that? No, it's this is let me see if, yeah, but it'll only play back on my speaker. See, I can turn my speaker up, but it'll only play back on my speaker. Yeah, but that's coming out of my computer. You'll also find a demonstration of using SPSS to do the same thing. Yeah. Okay, I guess that's going to be it. That's going to be it on that part. Okay, so let's go to, there's an Excel spreadsheet on Blackboard that's called Analysis of Variance Excel Demo. Okay, we don't want to get to the solution one. I'm going to open the background just so we can cheat on it if we need to. Or I can cheat on it if I need to. Why not? Okay, so I'm going to open up the one that's the demo itself, which is a blank page basically. So now, in these slides, in the lecture, if you had jumped ahead, you would have seen that there was an example that showed three groups that were sampled, and there was a comparison. You're going to go ahead and compare the means. Okay, so now I made up three groups here. There's three groups. I just gave them a silly name like Fred, Jim, and Alice. Maybe they're, like performance of some group that works with Fred and Jim and Alice or something like that. Maybe a performance thing, or maybe it's some sort of preference test or medical test or something like that. But let's just assume that these numbers represent samples of a numerical variable from each of these three groups named Fred, Jim, and Alice. The sample size is 5 for each group, as you can see here. Okay, so now the first thing that I might be interested in doing is calculating the means of these three groups. Okay, so I actually did it down here. Maybe I'll copy and paste. Maybe not. I'll just go ahead and do it. I'll bite the bullet and do it. Okay, I'm going to go down here and paste these in here, and paste Jim in here. And you guys can do this with me if you want. I'm just going to do a calculation of the mean and standard deviation and so on and so forth. Or actually, we might not quite get to standard deviation, but good. I think I got them all. Okay, so the mean here is going to be equal to the average of these 5 values, which comes out to be 1.8. And this is going to be equal to the average of these 5 values. And this is going to be equal to the average of these 5 values. Okay, so now I'm going to calculate well, we know that X bar, this is equal to 1.8 for Fred. Okay, and in fact, I'm going to put dollar signs in front of the B and these 16 so that when I copy it down, it keeps that number. Oops. See if that works. And I'm going to fill that down. Okay, and I'm going to do the same thing for Jim. That's equal to the number that's in this cell. Whoops. What did I just do there? Dollar sign. Dollar sign. Oh. Yeah, that makes it absolute addressing. That means it won't copy the number, like continue to down row by row to copy the number. It'll just put that exact number in there, not change it. Equals. Okay, I'm going to put in B32 if I just copy that down, it will try and fill it with all the other rows that are below it. Edit, watch this is going to do it wrong. Right? See, it fills in zeros because there's nothing in those columns. Had I gone in here and I said that was $B and $32, and when I copy that cell down, it'll just put that exact value into each one of the cells I copy it down into. Fill down. Okay, so now you guys remember how we calculated variability. First thing we did was calculate the difference between the mean and each value. So I'm just going ahead and do that. That's equal to 3 minus 1.8, and I'm going to copy that down. Then I took the square of the difference between each value to make sure that they were all the same size, same sign rather, equals x minus x bar times x minus x bar, and we get those numbers, and I'm going to fill that down. Okay, and then I'm going to add those all up together. Anybody remember what that was called? Now that I got it covered up? It's the sum of the squares of the differences, or we short name sum of squares. It's a measure of the variability. The more variable the numbers are from around the mean, the bigger that number is going to be. So this is a measure of variability. Sum of squares is a measure of variability. So I'm going to go ahead and just do it for the rest of the other two groups. Now, since notice I'm not being careful about whether I do x minus x bar or x bar minus x, because when I square it, it's going to be moot anyway, because there are going to be positive values. Okay, and then finally, I'll do the sum of squares here of all these numbers. And I'm going to do the same thing here. Okay. Okay, I'm just going to I'm going to cheat and take a quick look at my results just to make sure I get the same numbers. Down 5 point, whoops, I see a mistake. 2.8.
The middle.
Middle one, both of them. X bar minus, but what happened here? Oh yeah, look, we have, that's a couple of mistakes here, right? One is, oh, I copied this down twice, but I'm going to fix that in a second. Why is the middle one wrong? Let's see. 2.56.16. 3, that's negative 1.4, negative 1.3.4. Yeah, what happened there? Equals C19. This one's right. Oh, maybe this is rounded. It's probably format. Yeah, probably format, right? Let me try this again. Nope, did it again. Oh, you're right. There's something wrong here. Yeah. Okay.
It doesn't matter for most things because X aren't the same, but X would be 0 on that last one.
There we go. Hopefully you guys all got it right because you're doing it a little bit more carefully and slowly than I am. And over here, I copied the wrong values down here for Alice, I think. Right, what was Alice? Alice was this. And I should be able to fix that easily because these calculations should update themselves. So I think that's what we need. Okay, good. We're in good shape. All right, I just want to make sure that we were in good shape there. Okay, so these numbers here, they represent basically that sum of squares basically is determined by the amount of variability within the groups themselves. Okay, so now besides the variability within the groups themselves, we're also interested in the variability between the means of the groups. Okay, so let's go over here to this other side of the equation and let's take a look at what we have here. Now the overall means, let's see what the means were. Means were 1.8, 3.4, and 4.4. So these are the means themselves, right? Now, what's the mean of the means of the three groups? The means of the three groups is 3.2, right? That's just 1.8 plus 3.4 plus 4.4 divided by 5. I'm sorry, divided by 3, right? That's the mean of the means, right? So now we want to determine the variability of these means, right? How variable are the means themselves, right? Because the variability of the means is on the top part of our equation there, right? So let's calculate the variability of the mean. The overall mean is 3.2 for all the values. Now, there's a little bit of a cheat here because it happens that the sample sizes are the same. So instead of going through all the values, adding them up and dividing by the number of values that there are, what I was able to do is just take the differences between the overall mean and each individual mean, find the difference, square that difference, and multiply those by each of the number of values, the sample size in each one of the groups, right? So I didn't have to do it individually for each value. Okay, so now the differences squared is equal to 9.8, 0.2, and 7.2. So the sum of the squares of the differences between the means, between the mean for Jim, the mean for Fred, the mean for Alice, the sum of the squares of the differences for those means is 17.2. Now, okay, 17.2. So now, when we calculated the variability, we took the sum of squares and divided it by what number? Remember when we took the variability? What do we divide it by to get the sum of squares? What do we divide it by to get the variability? N minus 1. What is N minus 1? It's the degrees of freedom, right? So in the case of the mean, sum of the squares between the means, how many values do we have for means? We have 3, right? So what's the number of degrees of freedom? What's N minus 1 for the sum of squares of the means, the variability, in other words? What's that going to be? Degrees of freedom is number of groups minus 1, which is going to be 2. Okay, so the mean sum of squares between groups, that's really the variability between the groups, but now instead of calling it that, we're going to call it the mean sum of squares between groups, right? That's equal to 8.6. That is the variability between our means. Remember what we said was going to be the top of our F calculation? It was going to be a measure of the mean variability between the groups. The variability of the means between the groups, or in this language, mean sum of squares, right? So now we're going to do the same thing now for the sum of squares, for the sum of squares within the groups. Okay, so now in this case, we're looking at the variability for all of these groups, for all of these values. So that's going to be, let's see, we have the sum of squares for the differences within the group. So sum of squares for Fred is 2.8. The sum of squares for Jim was 5.2. And the sum of squares for all of these 5 values for Alice is 17.2. When we add them all together, oops, it's 25.2. That's all of the variabilities added together, all of the sum of squares for all of those values within the groups. Not the means, but within the groups. Okay, so that's equal to 25.2. Well, now, how many values are we working with there? We're working with 15 values within 3 groups. So our degree of freedom is going to be, for the first group, it's going to be 4 minus 1. Second group is going to be 4 minus 1. So third group is going to be 4 minus 1 because they're all sample size of 5. So in short, degrees of freedom is going to be number of subjects, which is 15, minus the number of groups, which is 3. So that's going to be 12. Okay, so we take our means, our variability. Now this is a measure of our variability. Remember, sum of squares divided by the degrees of freedom divided by n minus 1 is variability. Okay, this represents the variability within the groups, the actual numbers themselves within each group. That's going to go on the bottom of our equation. Okay, so our sum of squares is going to be, that's equal to, it turns out it's equal to 2.1. Our sum of squares is going to be a value that's equal to the mean sum of squares, measure of variability between the means, which is 8.6, divided by the mean sum of squares within the groups, okay, which turned out to be 2.1. So 8.6 divided by 2.1 is 4.095. Okay, so now we said to ourselves that F value, the larger that F value is, the higher our level of certainty is that there's a difference between the means of the populations, right? So is that F value big enough for us to reject the null hypothesis? First of all, what's our null hypothesis here for analysis of variance? Our null hypothesis is that there's no difference between the means of the populations. Mu1 equals mu2 equals mu3 equals mu4 equals mu5 equals mu6. What's our alternative hypothesis? That there is a difference between at least 2 of them anyway, right? It's going to be that there is some difference between at least 2 of the means of these populations. Okay, so now our F score comes out to be 4.095, right? And we know that there's this weird shaped distribution that represents what the probability of getting that big an F score is, right? So now, what would you think is the next step? Since you've already seen this with the t distribution and the z distribution and so on, especially with the t distribution, we need a value to compare it to. We need a critical value of f, a value of f that is big enough that we can reject the null hypothesis. Okay, so we need a table. We need something that gives us, or a value, or a reference in Excel or something like that, that will give us that critical value. Anybody can anybody think of what might impact what that critical value is going to be? Right. Well, the t-score. What did we have to know in order to find the critical value besides alpha's 5%? What else? Yeah, degrees of freedom, right? So it's likely that the sample size or degrees of freedom is going to have some impact on what our F score is, what our critical value F is going to be. So let's see if we can't find an F table. Okay, and I think, did I put one on Blackboard? No, I didn't put, there is one there, right? Okay, good. All right. All right, so let's go, let's take a look at this. Okay, so now, here we go. Now here's our analysis of variance distributions. It starts at 0, and here is the right tail probability. We want that to be less than 0.05. So this table is calibrated for 0.05. We wanted to do, if we want to do an alpha of 0.01, we'd need another table. We wouldn't use this table, right? But this is for 0.05. Okay, so now we have to apply the degrees of freedom to figure out which our value we should use from this table as our critical value F. The problem now is with the t-score, how many degrees of freedom do we have? We had 1 degree of freedom. Now we have 2 degrees. We have degrees of freedom for between the means, and we have number of degrees of freedom for within the groups. Remember what the degrees of freedom between the means was? How many means did we have? 3. So that's 2 degrees of freedom for the values between the means. You remember how many what our degrees of freedom was for the sample size for the values within the means within the groups? It was 12, right? It was 15 minus 3 for 3 groups, so it was 12. So our critical value is going to be, I'm going to go down to column 2. Critical value is going to be going down here, and it looks like our critical value is 3.89, right? So if we have an F score bigger than 3.89, we can reject the null hypothesis. So can we reject the null hypothesis in this case? Yes, we can, right? Right. Now, does that tell you, now you know that at least 2 of these means of these populations at a level of, with our statistical limit, our statistical criteria, less than 5% chance of an alpha error, we're at that level of certainty, we're sure that at least 2 of these means are different from one another. Does this test tell you which 2? No, it doesn't, does it? Right? Okay, and especially it'd be a little bit harder, even harder to tell if you were dealing with different sample sizes within the groups, because then, or the different variabilities within the groups, right? Could be one group is really tight, it's close to another group, but it's really tight, very small variability, so it's easier, it's more likely to be that population to be different, mean that population to be different. So really, it's kind of hard to tell from what we've done right now. I mean, based on the fact that these sample sizes are pretty similar, it kind of looks like maybe it's likely that Fred is different from Alice, right? That those are probably 2. But this doesn't necessarily tell you which of the means are different. Okay. To do that, we have to do some additional tests. Okay, we have to do some other comparisons. I'm gonna move this over to the PC because I don't have SPSS running on my machine, unfortunately. I'm going to move over to the PC now, and I'm going to import this data into SPSS. In fact, there's another, if you want to open SPSS, this same data is summarized in another file that you can import in, that you can open in SPSS. I'll show you that file. Okay, that would be SPSS demo for Innova.sav. That's the SPSS file. If you want to see an Excel version of it or a tab delimited version of it, you can see it here. You could use this tab delimited version for instance, for R. If you look at this, group 1 is, I believe that could be Jim or something like that. Group 2 is the variability under column B is the group variable, Jim, Alice, Fred, whatever, and the actual measurement within each of those group is the variability that I call measurement here. Okay, so you can see that there's 3 groups, each with 5 measurements, each with 5 a sample of size 5. Okay, so we're gonna open that in SPSS, and I'm gonna hand over this demo to, if I can, I'm gonna hand over this demo to the other machine here, and I think that's going to be AV. Yes. Okay, and I'm going to make AV the presenter. Okay. Okay, so cross your fingers. So now that should be our presenter. So I'm going to give this a try. Okay, and it says show my screen. Okay. How's it showing the screen? It is showing the screen, right? Let me get this out of the way so I can see it on mine too. Okay, so first thing I'm going to do is I'm going to go to Blackboard and download that file because I didn't have a chance. You guys got down here so quick that I didn't have a chance to. There's something going on outside. You guys noticed that there were all those fire engines parked on the street? I had to go out there and check it out because my car's parked right there. And I didn't want to run the hoses through my window. I think they have some sort of meeting at the school next door with the fire department, or there's I understand the mayor may be there as well. All right. Get this moved over a little bit. Okay, let me log in here. Okay, so I'm just going to grab the Excel file, the SPSS file. And I'll drop it on the desktop. Okay, and then double click it to open the SPSS. You guys can open it in your version as well. Now, I don't remember if this is coded. Did you guys open it already? Is it coded? Okay. There we go. Here it is open. I'm going to go to the variable view. And in fact, it is coded. We can see that measurement is a numerical variable. I should change this over here, right? Just so it knows it's a scalar variable. It may not do, the reason why it thought it was a nominal variable is because the numbers were so small, 1, 2, 3, 4, 5, right? The values that I put in there, and they were whole numbers. SPSS kind of makes this judgment when it sets up when you open the file, when you first set it up, it makes this judgment. Does this look like scalar or numerical data, or does it look like a categorical data? And when it saw only 1, 2, 3, 4, 5 as the values, whole numbers, it said, oh, maybe those are groups, not actual numbers. But we want to let it know that that's scalar. Those are numerical variables for the measurement. The groups, though, are nominal, right? The groups are group 1, group 2, and group 3. If I click at the values, right, I can see that we assign the value 1 to Fred, 2 to the group Jim, and 3 to group Alice. Okay, so I'm going to go back to the data view, and we can see the groups there. If I want, I can go up to view here and tell it to show me the value labels. So I can see which of those values go with which groups. And if you check, this is the same numbers as we had in the Excel spreadsheet. Okay, so now I want to do an analysis here. I want to do this analysis of variance to determine if the mean of the population from which Fred is drawn, the group Fred is drawn, and the mean for the population Jim, and the mean for the population Alice, if those three means are different or if the means are all the same. My null hypothesis, the mean for group Fred, for population Fred, mean for population Jim, mean for population Alice are all equal. All three of those are equal. They're not different from one another. Okay, so I have to I have to go ahead and perform an analysis. So I'm going to go up to the top here. I'm going to click Analyze. And let me bring this a little closer so the guys online can hear me a little bit better as well. Okay, I'm going to go up to analyze. I'm going to go up to, well, what are we doing here? We're doing analysis of variance. But we know now analysis of variance is really just a tool for comparing means. So I'm going to go to compare means. And if I go to analysis of variance, if I go to compare means, I see one of the selections is one-way analysis of variance. We'll worry about one-way means, what one-way means later on. So here we are. So now it's asking us to fill in these two boxes. One of them is the dependent list. That's the actual values that we're analyzing, the numerical variable. And then it asks for factor, and we know already from the t-test that by factor it means which of these variables identifies the groups, right? So in other words, we know that the groups are identified by the variable group. Okay, it doesn't ask me this time to identify the two groups that I want to do the analysis for, because it's going to do the analysis for all of the means, not just two of them. Remember in the t-test, when we moved the group, when we moved the variable that identified the group in there, it asked you to identify it, and so that you could tell it, group 1 and group 2 is what we want to compare the means on. Well, that's in case you had more than two groups. For instance, in this case, we have more than two groups. We could do a t-test if we wanted to between Alice and Jim, between group 1 and group 3. And in the t-test, we would be forced to identify group 1 and group 3. Here, it knows we're going to compare all the means at once, so we don't have to identify it. Just tell us that the groups are available in this column here, this variable here called group, and the numbers themselves are available in the variable called measurement. Okay, so now I'm going to go ahead and I am going to run this analysis of variance. We're going to go up here to these other buttons in a moment. I'm going to click OK, and let's see what we wind up getting. Okay, we get this output. I'm going to do it again so I can just bring it up higher so you guys can see it. Compare means. Come on. Analysis of variance, and say OK, it'll do it again. Okay, so this is up a little bit higher so we can see it. So let's take a look at this box, see what we have here. Now it's going to, the measurement that it's doing, the values that it's calculating is the variability or sum of squares between the groups and within the groups. Between the groups is the sum of squares for the variability between the three means themselves. You guys remember that number? It was 17.2, same one we calculated. The sum of squares within the groups is 25.2, same number we calculated for the variability for the 15 numbers that were within the groups themselves. So this is the variability within the groups. This is the variability between the groups, between the means. Okay, this is between the means. This is between the groups. Okay, so now the degrees of freedom. Well, between the means, there were three means, three groups. So the degrees of freedom are a number of groups minus 1, which is 2. Okay, the degrees of freedom for the values within the groups is the number of values that we had, which was 15, minus the number of groups, which is 15 minus 3, which is 12. So now the variability of the means is equal to the sum of squares divided by n minus 1, which is 2, or in other words, 8.6. That's what we call now the mean squares, really the variability between the means. The variability within the groups for all of the values within the groups is the sum of squares divided by the degrees of freedom, which is 13, which is 2.1. So now this is the top of our equation for F. This is the bottom of our, ratio for F. Okay, so 8 divided by 2.1 is 4.095. Okay, so now SPSS has the tables or whatever calculations it needs to do the calculation of our probability of getting that large a value for F for these degrees of freedoms. What's the probability that we would get that large a value F for these degrees of freedom if there was no difference between the means, any of these means? Well, the probability that that would occur would be about 4.4% of the time, 0.044. That's our p-value. That's the probability that we would have of rejecting the null hypothesis when there's no difference between the means. In other words, making an alpha error. What is our tolerance, did we say, for an alpha error? It was 5%, 0.05, right? So this p-value or significance is less than 5%. So there's less than 5% chance that we will be making an error by rejecting the null hypothesis here, making an alpha error. So we reject the null hypothesis and we accept the alternative hypothesis that there is a difference between these means. Okay, so now what's the next problem? What have we not found here in either case? We know that there's a difference between at least two of these means. Have we decided which two yet? No, so we got to do another series of tests. So now, if you notice, if I go up to analysis of variance, if I go to analyze, again, compare means. If I go to analysis of variance, okay, one of the things that's over here is post hoc. Anybody know what post hoc means in Latin? After the fact, right? So we're going to run a post hoc test after we've proven that after the fact it's been established that there is a difference between the means of these populations, at least to the level of certainty that we're satisfied with. We're going to run another test. So I'm going to click on post hoc. Okay, and this is going to give you a whole series of different possible methods of running post hoc tests. Okay, well, maybe we'll talk about this a little bit more detail, maybe next week, or maybe online a little bit or something like that. But there's a couple of different rationales for doing this. The simplest one is just to simply divide all the probabilities by adjust all of the probabilities for comparisons between the means, so that if there's three groups, instead of each comparison being 0.05, that instead it has to be 1/3 of that. In other words, kind of adjusting your level of certainty for the t-test so that it's distributed between each one of them, so you don't go beyond 5% chance of being wrong. Others use other kinds of ways of calculating whether or not these means are different from one another. So I'm gonna pick out two of the most commonly used ones, Bonferroni and Tukey. Okay, and I'm gonna say, okay, significance level, I could set that here. Remember before we only had that one chart, so we could only do it at 5%, alpha 5%. Okay, this you can actually change now if you wanted to, and see if you could prove it at 99% certainty, or an alpha of 0.01. So I'm going to click continue. I'm going to say, okay, it's going to run the analysis of variance again, but now it's going to do those post hoc tests again as well. So now I'm going to scroll up here and I'm going to take a look at these. Okay, so I'm going to start up here with this Tukey post hoc test. And what it does is it compares each one of the groups, the mean of each one of the groups, to the means of each of the other groups, and decides whether or not there's sufficient evidence to reject the null hypothesis that the means of those groups are the same. So let's go over here. The column we're really interested in is significance here. That's our probability of being wrong if we reject the null hypothesis that the mean for Jim is different than the mean for Fred, or is the same as the mean for Fred, or same as. So let's see. So we want this significance to be less than 0.05. So we can reject the null hypothesis that those two particular means are different. So let's see if we got any here. Fred and Jim, no. What is that? That's 0.037. So it looks like we can say with less than 5% chance of being wrong if we reject the null hypothesis that the mean for Fred is different from the mean for Alice, because the p-value or significance is less than 0.05. Okay, now notice that what it does next is it actually calculates it for Jim and for Fred again. Of course, we get the same value that you got before, right? It just looks at every permutation. So it actually does, it actually presents each test twice. I'm not sure why it does that, but SPSS does that in a lot of cases. Okay, so now, and in fact, if you look again, comparing Fred and Alice is the same thing as comparing Alice and Fred, and you actually do get the same values. Let's see if the other test agrees with that. Well, in fact, Fred and Alice, again, you would reject that null hypothesis. You would say that the mean for the population identified as Fred is different from the mean for the population that's identified as Alice. Okay, both of them agree. Do they both agree at the same level of probability? No, so it's a little tricky, right? There's a few different methods that you can use. Maybe next week in lecture, maybe Levi will discuss like why you would choose one method over another. So anyway, so now notice using SPSS, we got the same values we did when we calculated these things using Excel. So there's not really a lot of mystery to this. We actually saw how the F value was calculated. It's a pretty simple, straightforward calculation. It can get a little bit, confusing because a lot of numbers flying around, especially if there's larger groups and more groups and larger sample sizes and so on and so forth. But it's not anything terribly exotic, right? And we can certainly speed up the process by doing an analysis in SPSS. And for our purposes anyway, we need SPSS to perform those post hoc tests, unless we really want to get into a lot of trouble here. Okay, so any questions about that? So it's kind of cool, right? You have a method of using variability to tell whether means are different. So now you guys know